here we're being asked to calculate a volume. Now, if I use the word volume, remember that means geometric volume. My answer is positive. Okay, volume of a tetrahedron, that's just a shape that has four sides, each of which is a triangle. And we're being told it's bounded by the plane x plus y plus z equals 1 and the three coordinate planes. So pretty much I'm going to have a shape where I'm going to have a triangle in each one of these planes that makes up one of those sides. Okay. Now, I want to have a picture of what this looks like because I really need to visualize it in order to be able to set up my limits of integration. And it's the setup that's the trickier part with a lot of these integrals. We will see some complicated integrals, but I think many of you are going to find that the hardest part of integration is getting the problem set up. Now, if I'm looking at this being bounded by the coordinate planes in this plane, I'll find the triangular section of this plane that's my cross section if I just find the 3 points where this intersects the 3 axes. So it would intersect the x-axis when y and z are both 0. That would make x -1. So we'll have a point back here at -1, 0, 0. Okay. And then it'll intersect the y-axis when x and z are 0, so that would make y -1. So that's going to be this point 0, -1, 0. And then we'll intersect the z-axis when x and y are 0. So that's going to be 0, 0, -1. Now if I connect these dots here, you'll notice I was sort of drawing a triangle. Now it's a little bit tricky to see. That's actually all lying now below the xy coordinate plane, and I'm seeing this triangular section underneath that right there. What's happening is I can sort of see here, let's see, 4 different triangles. So this triangle is on this plane right here. Here's the triangle in the xy plane that I have. There's the origin, my x-axis, my y-axis, and the point connecting those intersects. Once I shade that, I can sort of see that it looks like this is lying below that. This right here would be the triangular section of the y-z plane that we're seeing, and this right here is the triangular section of the xz plane that we're seeing. Okay, excellent. Now, this lies below the xy plane, but I was not asked to find sine volume. I was asked to find volume, so I'm not just going to be integrating the function that gives me that bottom surface. If I did that, I would get negative sine volume. Remember, when we're finding volume, that's going to be the double integral over d of top minus bottom dA. I'm going to choose to call this region D here. It would be totally fine to call it R. I'm free to name it whatever I want to. I did notice, and I'd forgotten that they did this, I apologize. I did notice that the book does seem to switch to calling the regions D now that they're not rectangular, but it doesn't matter. Lots of other books call regions R when they're any sort of region. Okay. Okay, excellent. So, let's see. While we're talking about the top and the bottom, let's go ahead and get that. The top surface is 0. That's z equals 0 right there. That's the xy plane, is the top surface. What I'm subtracting is the bottom surface, which is going to be the part that's on this plane. Now here, I was given a perfectly valid equation for a plane, but it wasn't given to me as a function, so I'd need to solve for z. So I'd say z is equal to -1 minus x minus y. Okay. So top minus bottom is going to be 0 minus -1 minus x minus y, and we're integrating that over this region D. Of course, what that's going to do is that's going to take these negative z values, and we're just going to change the sign. So we're going to end up integrating over D, +1 plus x plus y dA. Okay, excellent. Now, these were negative z values. I didn't mean to imply that each of these terms was negative, because the opposite of x, I can see is actually going to be positive, and the opposite of y is actually going to be positive. But this whole thing was my z value, which is putting me below the xy plane. Okay, so now I need to set up my limits of integration. So I'm going to draw another picture just in the xy plane. And so here, I just need to be careful because x and y have a different orientation here. On the x-axis, we were intercepting when our x value was -1. And on our y-axis, we were intercepting when our y value was -1. So this triangle that I've shaded in green looks like this in the xy plane. Looks like that's either type 1 or type 2. I always like to slice things vertically if I can, so that my x values are constant and it's my y values that are functions of x. So, let's see. I'm going to need to get the equation for that line. I can see we're going down 1 and over 1, so we're going to have a slope of -1. And it looks like the y-intercept, so it'll be -x, and then the y-intercept is -1. Okay. So my inside integral is going to go from the bottom of the slice, -x minus 1, to the top of the slice, which is where y is 0. We've determined that top minus bottom is 1 plus x plus y. And here we're integrating dy. Then we multiply that cross-sectional area by the thickness of the slice. We add up the slices and we integrate. And it looks like the slices went from an x value of -1 to an x value of 0. At -1, we don't have much of a wall because the floor and the ceiling are meeting there. Okay, so let me just erase this left side of the board so we've got some room to work. All right, so from -1 to 0, integrating with respect to y, I'm going to get y plus xy plus y squared over 2. And we're evaluating that between -x minus 1 and 0, and then we'll integrate with respect to x. Okay, so that's going to be the integral from -1 to 0. I plug in 0 first, and then I subtract what I get when I plug in -x minus 1. Be very careful with that order. This gives me nothing, but I'm subtracting from that. Okay. So, y becomes -x minus 1 plus x times -x minus 1 plus -x minus 1 squared over 2, and we'll be integrating all of that with respect to x. Integral -1 to 0 of, I'm going to just simplify what's in here first, and then in my next step, I'll go through and distribute that negative. So we've got a -x minus 1 minus x squared minus x plus, if I FOIL out -x minus 1 squared, that's going to give me x squared plus 2x plus 1, and that's all over 2. So what I'm going to do now is two things at once. I'm going to consolidate any like terms and then distribute that negative. So let's see. For the x's, looks like I've got a -x and a -x. And here, this is a 2x over 2 that I'll be getting. So that's a plus x. That's going to be a total inside here of a -x. Distributing that negative, it becomes an x. For the constants, I've got a -1, and it looks like this is going to give me a positive 1/2. So inside of these brackets, I've got a -1/2. Distributing that negative sign is going to make it a positive 1/2. And then if I look at the x squareds, I've got a -x squared, and that's going to give me a positive x squared over 2. So inside the brackets, I've got a -x squared over 2. Distributing that negative makes it a positive x squared over 2. Okay, so that's going to give me x squared over 2 plus 1/2 x plus x cubed over 6. And all of that is evaluated between 0 and -1. Okay. Again, I'm plugging in 0 first. Whoops, this is 1/2 x. Plugging in 0 first, so I'm going to get 0 minus what I get at -1. Now what I get at -1 is going to be 1/2 minus 1/2 minus 1/6. Okay. The 1/2 minus 1/2 will cancel, so we have just -1/6. We're taking the opposite of that, and we got 1/6. Huh, I'm so relieved we got a positive number because we were calculating a volume. There were a lot of places I could have made a careless sign error along here. I don't think I did. I got a positive result. Now, that doesn't guarantee that I did everything perfectly because there are, of course, more than one positive number in the world. Remember, if you got a negative, do not submit that as a reasonable answer, and do not just assume that the mistake you made was a sign error so that you've got the opposite of the right answer. Go back and try to find the mistake. If not, if you can't find it and you're out of time, write me a note saying, hey, I know my answer is wrong, but I don't want to make an additional mistake of telling you that that's a reasonable answer, or of assuming that the mistake I made was just a sign error and I got the opposite of the right answer, because there are lots of different mistakes I could have made. Okay? So if you tell me that, I will dock you for whatever mistake you made in getting that negative answer, but I will not dock you for the second mistake of either pretending that's a reasonable answer or assuming that your mistake led you to get the exact opposite of the right answer. Because you might have gotten a different wrong answer. There are lots of wrong answers you could get.